So, where is it? The recording not rushed yet. It'll take some time. The recording is still. Okay, recording start already. Okay. So they ask you to design a 3-input encoder. There's A3, A2, and A1. If A3 is the lowest priority, A1 is the highest priority. The output is Y2 and Y1. Okay. If the input priority A3 is encoded is 11, A2 is 10, A1 is 01. Okay. So A3, A1 has the highest priority. Construct the truth table, get the Boolean expression, use the Karnaugh map, verify the circuit. Okay. All right. So this is the Karnaugh map, truth table for the 3-bit encoder. Okay. So you can see 000 XX. So you don't care. All right. You don't care about Y2 and Y1. The output will be 0 V. That means it's invalid. Then if it's the input only A3, 1, then the output will be 3. Okay, it's valid. Then if it's 1, 0, the output will also be 1, 0. If it's 1, 1, the output will still be 1, 0 because A2 has a higher priority. If A1 is 1, then the output will be 0, 1. Okay. Output will be 0, 1. You can see here. Or 0, 1 because A1 took the priority. From here, you draw the Karnaugh map. So this is the Karnaugh map. Then from the Karnaugh map, you get the Boolean expression. Then from this Boolean expression, you can build the circuit. Okay? Pretty straightforward because they ask you to build the basic logic gates. All right? So you can build the circuit from this Boolean expression. No problem. Okay, question 2. Design a 3 to 8 decoder circuit using 74139 IC. It's a 2 to 4 line decoder and other IC. All right. Form the truth table from a higher order decoder. Then design a high order decoder using a lower order decoder. Draw the logic diagram. Verify the truth table. Okay. So this is the truth table for the 3 to 8 decoder. So if it's this is the input 0, 0, 0. This is the output. This one is the input. This is the output. Right? Maybe you can add another line. Can we? Cannot add another line. Okay. So never mind. This one is all these are the input. So these are the input. These are the output. You see 0, 0, 0. Maybe you can change the color. Can we change the color? Hold on. Light blue. Never mind. So you can see if it's 0, 0, 0, Y0. If it's 0, 0, 1, there will be Y1. So this is active flow. Okay. So this is the internal circuit or the 74139. This is a active low circuit. Okay, you have the enable pin here, and you have the selector, the input. Let's say the input is 1, 1. The input is 1, 1. All right. You enable. Enable will be enable bar, isn't it? So it will be 0. So when it's 0, goes to here, it will be 1. Okay. So when all these three are 1, the output will be 0. Okay. So this enable pin must be 0. Okay. Because it's enable bar. Okay. Then you look at the data sheet, you can see that only when the enable bar is low, then the output will depend on the input. Okay. If the enable bar is high, all the output is high. So this is an active low circuit. Okay, active low circuit. Right. So this is how you're going to connect a 2 to 4 decoder and 2 to 4 decoder to become 1 times 3 to 8 decoder. So this is how you combine 2 to 4, 2 unit of 2 to 4 decoder and become 1 unit of 3 to 8 decoder. So you can see the enable pin. If the enable is 0, when you invert it, it will be 1. Okay. So over here, so if it's anything that is 0, 0, it will not activate the lower portion. Anything that is 1, 0, it will not activate the higher portion. So all the high portion will be high or high. Okay. If all the lower portion will be all high. If it's 0xx, then all the higher portion here will be all high. All right. So this is how the circuit look like. Okay, after you connect. All right. So from here you can see this is the pin 2, pin 3, pin 1. Okay. So let me stop sharing for a while. Okay, and then let me open the digital. Okay, so open. Digital works up. So tutorial 5, A question 2. Open. So you can see here. All right, so this is 1. It is 0. Can you see the circuit or not? Can you see the circuit? And you see the okay. Red dot represent 1 while white dot represent 0. Yes. Yes. Red is 1, white is 0. So this is active low. So active low. So this 0, 1, 1, 3, 2, 4, 4, 5, 7, 6. Okay. Everything is given. Okay. So this is how. So when you click on this one, this is a circuit. Okay. All right. So okay. So this is how it's done. Okay. Then question number 3. Design a 2 full adder using a 2 half adder. So this is how the circuit will look like. Okay, they ask you to design using 2 half adder, using Nand and using NOR gate. Okay. So 2 half adder is like this. All right. So you get 1 half adder, 1 half adder. Then the carry one, you put another OR. Okay. So the circuit open. Oh, question 3. I mean question 3. A. So you can see here. This is the circuit for 1 half adder, another half adder here. So 2 half adder become 1 full adder. So you can 0, 0, 0. So this one is 1. Carry. Okay. This is the. Right. Then the next one is you want to use truth table, also can. So truth table, you can see if it's 0, 0, 0 is 0. If it's only 1, 0, 0, 1 or 0, 1, 0, then the sum will be 1. If there's 2, 1, then the carry will be 1. If there's 3, 1, the carry will be 1. So then from here, you build the Karnaugh map. Karnaugh map, okay. Karnaugh map using okay, this is the Karnaugh map. Then you get the formula for carry and for sum. The formula for carry and for sum is in the Karnaugh map. Okay. Okay. So you want it to be in the Nand Gate, Nand Gate. Then you must put it in SOP form. SOP form. Okay. Design the circuit. If you want NAND, then you have to start with SOP form. So this is the SOP form. C equals to XY from here. Okay. Then you put a double bar. Okay. Put a double bar. Then from here it become here. Then you can do the NAND gate. How do you jump from here to here? So let's say A, B bar, A plus B bar, okay, like this is equivalent to A bar times B bar. So if this one, A plus B plus C bar will be equivalent to this one, which is also equivalent to this one. So, thus. Okay. So it's a bit difficult for me to draw the digital works because most of the gates, there are only 2 input. Okay. So, therefore, we just show you the drawing. So from here, you can change to here based on this one. Okay. Based on this one, you can change from here to here. So for XY, this one, you put everything double bar together. Then you put this one bar. Okay. So this one, all the terms are the same, except you multiply and then each of the term you buy. So this is the S. So from this one, from here, then you can get the term, this one. Okay, so you can see S. So this is X bar, Y bar, Z bracket or bar. Okay, connected to this one. This is an AND gate with a NAND gate. All right, so this is a multiply with a NOT in front. Okay, with an inverter in front. Then this one is XYZ bracket bar. So you can see here. XYZ bracket bar. Okay, and then for C is C equals to XY bar. So we can this XY bar. So you can see this is X and this Y. All right. Another one is XZ. Okay. So this is how you implement using a NAND gate. If you want using a NOR gate, then you have to put it in product of some form. So based on the Karnaugh map, so C will be equals to X plus Y times X plus Z plus Y plus Z. So this one is X plus Y. All right. X plus Y. This one is X plus Z. And then the last one, the last one, okay, the last one will be Y plus Z. Okay, Y plus Z. Okay. So this is the product of some term. Then product of some term will be for S. This one will be this one. Okay, X plus Y plus Z. Okay, then this one is this one. Okay, you circle everything, then you get 4 of them. So after you get that, then from here, this is the formula. You do a double negation, and using the same formula, you can see is this one. Okay, so you can, this one is also equivalent to this one. Okay, bar, and C is equivalent to this one. Okay, by using this formula, it's straightforward. Okay, so then from here we can draw the circuit. You can see what is C. C is X plus Y bar. So here is X plus Y bar, X plus Z bar, Y plus Z bar. Then add together, then everything bar. Okay, the same thing goes to the upper part. So this is how you implement the using NOR gate. NOR gate. Okay. Any questions so far? Question 3 is the copy slide. I don't understand. You can say lah. Well, up to you lah. Okay, you have to write it down lah. Okay. Alright, I will explain more lah. Okay. Later, after the recording is done. Question 3, no scenario. No scenario lah. No scenario. Question 3. Full adder, where got scenario? No scenario. Okay. Alright. So now we do question 4. Question 4. Question 4. We have 4 input. W, X, Y, Z. And you have a function. If it's 1, 2, 4, 6, 7, 9, 11, 14, 15, then the output is 1. So there's 3 questions here. First, you need to use the mux 8 times 1 multiplexer. Second, you have to use 16 times 1 multiplexer. Third, you have to use 16 using the suitable decoder. So suitable decoder means 4 to 16 decoder. OR gate. Okay, so I cannot find the simulator for the multiplexer. So it's only theory only lah, as far as the multiplexer is concerned. Okay, right? So this is the truth table. So you can see 0, 0, 0, and this is the M function. Okay, the M. Okay, Z and M. Okay, how you get the M? The M you get from here. From here you can get it. Okay. Okay, from here. So M equals to 1. When it's 1, maybe we can put it, the question here. Then it becomes more precise. Okay. In one slide. So the value of M, actually, with respect to Z, the value of M with respect to Z. So let's say if you cover up everything. You see Z and M only. So 0, 0, 1, 1. So M will be equal to Z. Then in this case 0, 1, 1, 1, 1, 0. So M is equal to bar. Okay. All right. So you can see here. So the value of M can either be Z bar, 0 or 1. Either all these 4 values. So you can remove the Z from the multiplexer. Just add extra circuit to cater for Z. All right. So this is the value. When M equals to Z, when it is 0, 4, and 5. 0, 4, and 5. Okay. So if you remove this one. If you remove this one, okay, then you can see 0, 0, 0. So it's 0. Okay, it's only 8 combination. Okay, these two is the same. W, X, Y is also 1, 1. Okay, it's the same. So from 16 combination, it become 8 combination because you already removed the Z. Okay, so next. So then what will happen? You just do the circuit. This is the drawing. So you can see M equals to Z. Okay, so you have W, X, Y will be here. So W, X, Y will be here. So you connect W, X, Y to the selector. This is the selector of the multiplexer. Since you are using the lower portion of the multiplexer, you use here. Then when Z, M equals to Z, when it's 0, 4, and 5. Okay, so you put the Z here, connect to 4, connect to 4, connect to 0, okay, and connect to 5, okay. So you can see Z is connected to 0, 4, and 5, okay. Then you can see M equals to Z bar, Z bar. So when W, X, Y equals to 1 and 2, so you connect to the inverter, Z connect to the inverter, then put 1 and 2, pin 1 and 2, connect to the multiplexer. Then M equals to 1, so 1 is VCC, so you connect in pin 3 and pin 7. Okay, pin 3 and pin 7. Then ground, pin 6, so you connect ground to pin 6, and you also connect ground, you don't connect ground, because this is a, I don't know what kind of multiplexer is it, okay? It's either, I think ground, it's ground, okay? 2 times 1 multiplexer, okay? If it's if there's a bubble here, maybe you need to connect to the VCC, okay? So this is the first question. The second question, if you're using 16 times 1 multiplexer, then just use the multiplexer only. So you can see M equals to 1. On this occasion, M is equals to 1. So what will happen? Over here, pin, you can see the function. Where's the function? Okay, this is the function. So what will happen? You put pin 1, 2, 4, you can see here. All the pin you connect to the VCC. The rest of the pin you put it to the ground. Okay, then you can get the output F, which you want. Okay, you put in, this is the input. Input W also you put here. Okay. Okay. All right. So this is, oops. Okay, this is the 16 times 1. Okay. Then for the next one, you use a 4 to 16 decoder. So 4 to 16 decoder, this is how it looks like. You have here, this is the 4 to 16 decoder. You have this function. And because this is active low, so you need to put in the inverter and then combine everything and get the function F here. So I have the circuit here. Open question 4. Part 3. Question 4, part 3. Open. Okay. So first you ignore the bottom part first. Okay. You ignore the bottom part first. You can see the input. The input, okay, put all 0. So you can see Y0 is here. Then you put 1, 3, 2, 6, 7, 5, 4. Okay. Then you can put, you can see here 12, 8, 9, 11, everything here. Okay. All right. Since you want 1, when it's 1, okay, when it's 1, you can put over here negative. So here is 1. It become 1, 1. You can see the line. The line is 1 now. Okay, when it's 2, 3. We can see 3 cannot. Okay, when you see 2, you can see 2. The line here like this. So it become like this. Okay, so this is how you do a 16 times 1 decoder. Because this is an active low chip, so you must add the inverter here. Okay, the inverter must be added here. Okay, if it's an active high chip, then this you don't need to have this inverter. Less work. Okay. Any question? So far so good. Smooth and steady. Smooth sailing, huh? Okay. Smooth sailing, huh? Okay. Question 4 done. Okay. Question 5. Okay. Gray code to binary code converter. Okay. Gray to binary code and binary to gray code. Okay. So these are gray to binary. So first you do binary to gray code first. Easier to understand. So this is the binary value. You can understand it. 0, 1 until 7. Okay. So you translate into gray code. 0 equals to 0, 1 equals to 1. Okay. So in gray code, only 1 bit can change only 1 time. So what will happen? If it's 2, then it becomes 0, 1, 1. If it's 3, you only need to change 1 bit only in it. So it becomes 0, 1, 0. If it's 4, then it's 1, 1, 0. If it's 5, it's 1, 1, 1. Then over here is 1, 0, 1 and 1, 0, 0. So you have covered everything. Okay. This is how you change from binary to gray code. So from here, then you can swap it, rearrange the position. You can get from gray code to binary. Gray code to binary is a bit confusing, okay, to learn. Okay, binary to gray code is easy. All right. Then from here, all right, gray code to binary. Okay, this is a gray code to binary. So you have arranged the truth table here. So from here, you can see the runoff map. B2 equals to G2. You can circle. Maybe you can put here bigger a bit. Here maybe 20. Oh, too big. 16. 12 lah. Okay. Okay. Then you can circle. You can see here. Okay. So you can see here B2 equals to G2. Then you have B1 equals to G2 XOR G1. And B0 equals to G2 XOR G1 XOR G0. Okay. Then this is the circuit diagram for binary, gray code to binary. Okay. This is a circuit diagram. Okay. Then from binary to gray code, so binary to gray code, you get from the truth table from here, you get the Karnaugh map. Karnaugh map, you simplify. Oh, okay. Something is wrong here. Something is wrong here. It's not all 1. Okay, you can see, all right. And this 1, 1. Okay, so from here you can see you get the Boolean function. Then you draw the circuit. Okay, clear? Any question? So far, so good. Smooth and steady. Smooth and steady. Okay. Yeah. Okay. Now question. Okay. BCD to X3 code. So BCD to X3 code. So SS3. What do you mean by SS? SS mean lebih. Mean lebih tiga. Okay. In Malay means lebih tiga lah. Mean, alright. So you get the truth table first. So from the truth table, all right, so you represent the BCD, right, as A, B, C, D lah. Okay, A is the 8-bit, B is the 4, and so on lah. Okay, so you draw the truth table, okay, and then the SS bit, SS3 is plus 3 extra, 0 plus 3, 1 plus 3 is 4, and so on. Okay, so from here, you draw the Karnaugh map. Okay, you get the Karnaugh map. The Karnaugh map, W equals to, so this one is from here, you can see first 5 is 0, so you get the Karnaugh map, you get W equals to A plus B brackets B times BC plus BD lah, basically. Then you get the Karnaugh map for the second one. Second one you manage to get, so it's this one, okay, when you do the circle, everything. The third one, Karnaugh map, so the Karnaugh map for the third one, Y will be equals to what? Equals to here CD bar. Okay, because this one row. Okay, and this another row here, CD plus CD. Okay, that's Y. Okay, and then over here, Z. What is Z? What is Z? Okay, let's see Z. Z. Oh, Z is even easy. It's D bar. Just D bar. Okay, how do you get D bar? Okay, so this D bar. Okay, so now you got the function already. So this one is what? This is a bit messy lah. Or maybe this one is, we can further simplify. This one is a bit messy, so I think we have to simplify further. So this one will be A. So let's do the circle here. So this one will be A. These two. Delete everything. Okay. So let's do the circle. So what is this one? What's this one? This one is B bar. B bar. B bar and what? C. C plus B bar D. Okay. So you move the circle a bit. So B bar B. All right. So it's from here to here. Okay. All right. So it will be B bar C plus D. Okay. So we already cover everything here. Okay. We already cover everything here. So then we only need to cover here. We only need to cover here. So this one. So this is what? This is plus B C D. Okay. This more simplified solution. Okay. Once you get the Karnaugh map, then you get the Boolean expression. Expression is what? What do you have the Boolean expression? So the Boolean expression. Okay. Okay, you get the Boolean expression. So can you do the circuit? Easy lah, correct? Okay, can the circuit I don't show to you I don't show to you you can do by yourself okay, because in the question, let's see in the question what did they ask? Design a code converter. They say design only. Okay, the circuit easy lah. You just give AND and OR gates, AND OR and NOT gates. Enough lah. Okay. Okay, then you can build the circuit. Then it's done. Okay. So far so good. Okay. Can Any question? Any question? No Then I'll stop the recording. Then we will ask the specific other thing lah. Okay. I stop the recording now Okay. Then I upload this. No need truth table for the. This is the truth table lah. This is the truth table. Okay. I put the truth table and the Karnaugh map at the same place because then you can refer. Easy for you to refer. Okay. Okay. What else? Yeah. Of course. Pandai pun Edri. Okay. So I stop the recording now. Remember, like, share, and subscribe. Okay.